we're moving to the middle part of this chapter. This chapter will be divided up into 3 parts. So the middle part of the chapter is sections 9.4, 9.5, and 9.6. And this is going to be the next 5 series tests for convergence that you'll learn. So first to start, just a quick recap of some of the tests that you've already done. So for the first one, these are all looking at things that we used over the course of the first 3 sections. The first one, this is an example of a geometric series. So it's a geometric series where your ratio is a half, which is less than 1. So this one would converge using the geo test, the geometric test. Next one, when you have n to a power in the bottom, that is a p series. Your p is 3, which is bigger than 1. So this one will also converge by the p series test. Keep in mind, for p series, you could also do an integration test. It just takes more work. And then the last one, this is one that we can take the limit. Since it has the same degree, my limit as I go to infinity of this value would be 5 over 3, since the degrees are the same. That is not 0, so this one would diverge by the nth term test, which says if you get any limit that is not 0, it will diverge. So moving on to our tests today. Today, we're going to work with things that are called comparison tests. Essentially, we're going to be able to utilize what we already know, basic p-series, basic geometric, and take series that are really similar to those and do a comparison to help us kind of broaden our horizons as far as what we are now able to determine if it converges or diverges. So here is the first test. This is test number 6. So I am numbering. There will be 10 total. We've done 5 so far. This is number 6. This test is called the direct comparison test. I often just abbreviate it DC for direct comparison. We have 2 series. We have a series that's given, and then we have a comparison series. We're going to refer to the B sub n as the larger of the 2 series, and we will talk about how you tell if something's larger or smaller. And we're going to refer to the A sub n as being the smaller of the 2 series. And here are 2 things that I know about direct comparison. I know that if I can prove that the larger one converges, then the smaller one has to as well, which should make sense, because if the larger one is converging to a finite number, then the one that's smaller must also converge to some sort of finite number. The other thing that I know is if I know that the smaller of the 2 series will diverge, then the larger one must diverge as well. Again, the idea that the smaller one is going to get bigger and bigger and bigger, well, then of course the larger one must also do the same. And I kind of summarize it just in this phrasing. If the larger converge, the smaller converge. If the smaller diverges, then the larger diverges. I can't say anything other than those things. So I can't say, well, if the smaller converges, I know something, or if the larger diverges, I know something. So it can only work in these 2 situations. When we do the direct comparison test, we often look at a very basic p-series or a very basic geometric series to do the comparison to. So let me show you how this works. So if you look at this one, the series 1 over 2 plus 3 to the n, it looks really similar to 1 over 3 to the n. So we're going to compare it to something very basic. In this case, we're going to compare it to a very basic geometric series. And what I know about that is this series will always be bigger than the given one. And the reason I know that this one will always be bigger is the given one has extra stuff in the denominator. When I have extra stuff in the denominator and I divide by something that's bigger, I'm going to get a smaller value. So in this case, I know that the comparison one, the 1 over 3 to the n, is always going to end up bigger than the original series that's given. Well, what I know about this comparison series is I know it converges by the geometric test because your R value is a third. Your ratio is a third. And by direct comparison, if the larger one converges, then the smaller one must converge as well. So I can say that the given series, and I usually are real generic and just call it A sub n, converges by doing a direct comparison. Really, the key is what you compared it to, kind of that information over there. The next one is really similar to 2/3 to the n power. It also is very similar to a basic geometric series. I know that this is a geometric series that converges because R is 2/3. So this is another geometric series that converges. I also know that this one is going to be bigger than the given series, because the given series has extra stuff in the denominator. When I divide by something that's bigger in the denominator, I'm going to get a smaller value. So the given one is smaller than the one I'm comparing it to. Since the larger of the 2 series does converge, then we can say that the given series will also converge because I did a direct comparison. The last one, we're going to compare it to 1 over the square root of n, or 1 over n to the 1/2, because it's very similar to that. This one is a diverging p-series because my p-value is less than 1. I also know that this has got to be smaller than the given series. And the reason I know this one is smaller, when I subtract something in the denominator, when I create a smaller denominator, I create a bigger overall result because I'm lessening the denominator. So the comparison one, the 1 over n to the 1/2, is smaller. It also diverges. So I can say if the smaller one diverges, then therefore the given series must also diverge by doing a direct comparison. I will say, of the two tests I'm going to show you today, I actually use this one less. I feel like this one kind of takes a little time because you have to figure out which one's bigger and which one's smaller. And the next test I'm going to show you, you don't have those limitations, so you're able to do a little bit more with it. I have seen questions on the AP test where they're very generic, and they'll say something like, this series is bigger than this series. If I know that this series converges, what can I assume about the other series? So it kind of makes you understand it in a very generic sense. Here's our second test of the day. Our second and final test of the day is called the limit comparison test. It is the 7th test that we've learned. I usually abbreviate it LC. With the limit comparison test, you are going to be looking at a given series, which we can just call the a sub n series, and we are looking at a comparison series. It should be something that's very similar to it. Both of these series are positive. The idea here is if we can compare it to something where when I take the limit of the original and divide it by the comparison, if I can get a finite number, any finite number, when I take that limit, then that means the two series have to act the same. So if the comparison series diverges, then the original diverges. If the comparison series converges, then the original series converges. Here's the nice thing with this one. You have a lot of control. The idea is you want to compare it to something where I will get a finite limit. The goal is to compare it to something that when I take your a sub n, your original, and I divide it by your comparison, I get the same degree. If I have the same degree on the top and bottom, then I know my limit will be that finite number. So I think the best way to explain it is to just show you some basic comparisons. What would you compare it to make it work? And then we'll actually go through and do some. So this column is your given series, and then over here would be what would be ideal to compare it to. So for my given series, the first one, the 1 over 3n squared, the key here is it's to the second power. I want to compare it to something that's also the second power in the denominator so that when I divide by it, think about what happens when I divide by 1 over n squared. I'm actually going to be multiplying by the reciprocal, so I'm going to end up having an n squared on the top. Then I will have the same degree and I'll be able to get a finite limit because they'll both be n squared. Same thing for the next one. I currently have an n to the 1/2 in the bottom. If I can compare it to something that also has an n to the 1/2 to the bottom, so 1 over a square root of n, then when I take this one and divide it by this one, I will get both of them to have the same degree. With the third one, so I have an n squared on the top, I have an n to the 5th on the bottom. I want to compare it to 1 over n cubed so that when I divide by this, or in other words, multiply by the reciprocal, I'm going to end up with an n to the 5th on top and an n to the 5th on the bottom, and that will give me a finite limit. For the last one, since I have a square root of n, or an n to the 1/2 on the top, and an n to the 1st on the bottom, I want to compare it to 1 over n to the 1/2, or 1 over the square root of n, so that when I divide by that fraction, I will multiply by the reciprocal, I'll get the same degree. So it works really, really nicely with p-series. It does also work with geometric, so I will show you the geometric as well. And again, to me, this test is way simpler to use because I can control what I'm comparing it to, and I don't have to check and see which one's bigger and which one's smaller. So I actually feel like this test is a little more flexible and easier to use. So here we go. So this is what you'll be given. You'll be given something that looks very similar to a basic p-series or to a basic geometric. What I need you to tell me is, what are you going to compare it to? So with this one, I want to compare it to something that has an n squared on the bottom. You can be really simple. You don't need to put a number on the top, just like a 1 over n squared is fine. What I know about this series is that it is a converging p-series because it has a p-value that's bigger than 1. Here's what's going to happen when I divide. When I take the limit of this original series divided by my comparison series, I'm going to get a 3n squared on the top, and I'm going to get a 1n squared on the bottom. So I'm going to get a 3. And what you can see is you can even kind of come up here and show what happens if I multiply by n squared over 1. That's the same as dividing by 1 over n squared. That's going to give me the same degree. Since I get a finite number, both of these series have to do the same thing. So therefore, my given series, and again, I usually call it a sub n, will have to converge because I used a limit comparison. And it will always do whatever the comparison series does. For the next one, I have an n to the 1/2 on the top. I have an n squared on the bottom. I want to compare it to 1 over n to the 3/2 so that when I divide by that or multiply by the reciprocal, I'm going to get the same degree on the top and bottom. This is also a converging p-series because it has a power that is bigger than 1. And if I take the limit of my original series divided by my comparison series, I am going to just get a limit of 1, which again is a finite number. So therefore, both series act the same so that we can say the original series will converge because I did a limit comparison. So let me show you how it works with a geometric, because it actually works the same way. If you have something that looks like a geometric series, it's really similar, but it maybe has extra stuff in the bottom or extra number on the top, we can compare it to the very basic geometric series. So we can compare it to just 1 over 2 to the n. We know that that is a converging geometric series. If I multiply this by the reciprocal, so if I multiply this by 2 to the n over 1, I actually can get the limit. You are basically looking at the leading coefficients of the exponential piece. So you have 4 2 to the n's on top, and you have a single 2 to the n on the bottom. So the limit of that, as I take those original and comparison, is just going to be 4. And again, that's a finite number, so we can say the original series will converge by doing a limit comparison. So it does work with geometric as well. I feel like I use it the most with comparing with p-series, but it will work with geometric, and you don't have that limitation of worrying about which one's bigger and which one's smaller. So let me just show you a couple mixed examples. For the first one, this is one of the few times that I actually would struggle to do a limit comparison because that natural log kind of throws a wrench into it. So this one, it would be better to do a direct comparison. I'm going to compare it to just 1 over n plus 1. Here's what I know about 1 over n plus 1, and I actually can know a couple things. I could integrate 1 over n plus 1 and get a natural log. I could actually compare 1 over n plus 1 to 1 over n. I could do like a double comparison. Either way, I know this is going to diverge. Probably the quickest way is to think about what you would get when you integrate it. You would get a natural log when you integrate it. I know that this 1 over n plus 1 is always going to be smaller than the natural log of n over n plus 1 because I'm putting more stuff in the numerator here. So as I put a bigger and bigger numerator in, and natural log does get bigger as you go, I'm going to get a larger piece. So my comparison one, my 1 over n plus 1, is smaller. If the smaller one diverges, then we can say the original one also diverges by direct comparison. That's one of the few times that I actually use direct comparison and not limit comparison. Most other ones, I'm doing a limit comparison because I just find it to be much easier. The next one, I'm going to compare it to 1 over 3 to the n. 1 over 3 to the n is a converging geometric. If I multiply by the reciprocal, 3 to the n over 1, I'm going to get 2 3 to the n's over 1 3 to the n. So my limit, as I look at my original divided by my comparison, will be 2. Obviously, that's a finite number, so therefore both will be the same. So a sub n will also converge by doing a limit comparison. The next one, it may help to just think about what you get when you distribute. You end up with an n to the third in the bottom, so I want to compare it to 1 over n to the third. That is going to be a converging p-series. If I take the limit of the original series divided by the comparison series, I'm just going to end up with 1 because I'm going to have 1n cubed over 1m cubed. Obviously a finite number, so therefore we can say that the original series will converge as well by limit comparison. I like the comparison test because I feel like it takes your limited knowledge. Right now, you really only have those 5 tests to work with to start, and it allows it to expand that knowledge and start looking at things that are really close to a geometric series or really close to a p-series and allow us to do a comparison to be able to figure out how they act. So that's our 2 tests for today, test number 6 and test number 7, and that covers section 9.4.